Okay, folks, welcome to my talk on logistic regressions. This isn't an advanced talk, and it is most definitely not an exhaustive talk on the topic. So I'm going to cover what a logistic regression is. I'm going to tackle this from a very non-maths background because the wall of formula that you often see, I don't think helps you get an intuitive grasp of what a logistic regression is and what you can use it for. And then I'm going to go through some data preparation, what sort of models you might want to build, and then some valuation metrics at the end of it. So that'll give you a little bit of the whole workflow, but won't cover the breadth, won't cover everything in each bit along the way. So a bit about me. I started my own data science consultancy at the beginning of February, and I help organizations start doing data science. You can follow me on Locke on Twitter, and you can follow my blog on itsalocke.com. I do a lot of R posts, mainly. Okay, so logistic regression. What is a logistic regression? So a logistic regression allows us to perform a binary classification, but with a linear regression. So we're able to say how likely an outcome is, or we're able to say we predict it to be this outcome or this one. But most importantly, it's on one or more discrete classes. So linear regression, hopefully you've all done lines of best fit and everything. Linear regression allows us to basically plot our way through a bunch of variables with straight lines and end up with a prediction of a continuous value. And notionally, those values can become plus or minus infinity. Okay. So we need a transformation function for logistic regression because it doesn't make sense to have a continuous prediction for something that can only hold one or two, like a couple of values. So if we had a situation where we've got whether somebody survives or dies from, say, a cancer drug trial, then we don't want to be able to say they're very, very dead, or they're, like a Schrodinger's cat, they're 50% alive, 50% dead, well, it'd be great to say they're 110% alive, but it isn't very sensible. So we need to do something. We need to go from only being able to pick ones and zeros to being able to pick from a continuous range. So the first thing we can think of is, what could we do that moves us away from just ones and zeros? And the first thing is probability. We can say how likely someone is to survive. And when we do that, that gives us a 0 to 1 range. So all our outcomes where they didn't survive, each one might have a probability of survival that is hopefully pretty low. Whereas if somebody did survive, hopefully their probability of surviving from our model would be quite high. And we can say then, from a very simple classification, that if they had a sub 50% probability of surviving, then if we were doing just a discrete classification, we would say that they didn't survive as our prediction. If they had a probability greater than 50%, we could say that we would predict that they survived. The trouble is that with a probability, we're still getting a value between 0 and 1, which means if we get something outside that range, it doesn't make sense from a probability perspective. So previously, we could only allow the selection of the values 0 and 1. Now we can have a continuous range between 0 and 1, but we're still not at our plus or minus infinity. So now, how can we bust out of 0 to 1? And the first thing that we can do is take the odds of something happening. And all my LaTeX is not working right now, so I apologize. But the odds of something happening is the probability of it happening divided by the probability of it not happening, which means we can get, if somebody had a probability of surviving of 100%, then that would be 100 divided by 0, 1 divided by 0, so they'd have a plus infinity odds. Whereas if they had a probability of 0 of surviving, then they'd have an odds value of 0. So we've bust out of the in our positive range into plus infinity, but this still doesn't allow for sensible negative values. So the thing that we can do to make to generate sensible negative values is take the log of these odds. So the logit is the common name for the log of the odds. And when we take the log of the odds, we then get values that go from minus infinity to plus infinity. So anything that has a log, negative log, has a probability less than 50%, which would be in odds would be 50 divided by 50. So a probability of an odds of 1 and a log of 1 is 0. So in those circumstances, we can use the logit as our simple way of classifying things. And once we've got this logit and we get this continuous outcome prediction, we can then transform that either into a discrete classification, or we can go all the way back to a probability. So the probability is just a simple transformation away. And that allows us to use a continuous variable prediction of regression against a discrete outcome. And that's super handy for us because regression is a very fast algorithm that works over a lot of data. And it's a really simple model, so it's really easy to take the results, take the coefficients of the model, have them be interpretable, and then be able to put them into a production setting. So let's have a look. That's all the theory for today. Everything else is going to be fairly practical. So let's have a look at doing logistic regressions in R. Okay. Very simply, there is a function called GLM, and GLM allows us to run, is a function for running general linear models. So you can run a simple linear regression model using GLM. But I most commonly use GLM to do logistic regressions. So when we do that, we specify our outcome variable, our predictive variables, where the data is derived from, and then we say what family of linear model we want to run. So when we're doing something that is one or the other, it's a binomial outcome, and the link function is how it goes from that binomial outcome to our linear variable, our linear prediction. So we tell it that the link function is using that logit. Don't know how conversant you guys are with building models in R, so I just wanted to quickly run through how you would specify a model. So your outcome variable you always put on the left-hand side, and then to the right of a tilde you put any variables you want included in the model. So by default we have an intercept, and you can remove that by putting -1 on the right-hand side of your formula. If you want to use every variable to do a prediction, which of course risks overfitting but gives you an idea of the maximum accuracy you could get on your training data, you would use a full stop. You can consider variables independently by using a plus sign. You can look at their interactions by doing colon, and you can look at the interactions and the values independently by using an asterisk. And you can also make transformations as you go. Some useful parameters. So in addition to the basics that we added, when you're specifying a model, for it to go away and build a model, there's you need to think about how you handle missings. So by using the na.action, you can get it to just omit any rows which have missings. This means that you don't have to necessarily do any handling of them beforehand. And then, especially if you're working over a lot of data, the model X and Y parameters allow you to specify whether information about the model, sort of the data frame behind it and everything, gets returned back when you do a GLM. If these don't get returned back, then you don't have a duplicate copy of your data lying around, which makes it a much smaller object, which means you can generate more models in memory, or you can, if you store that model for reuse later, then it'll take up less space and it'll load up more quickly. So with R and the GLM function, there are some functions called coefficients, summary, fitted, predict, and residuals, which allow you to extract certain values from a model. So if we look at the model we ran earlier, when we run it, we get some information about it, but we can also get some specific bits and pieces about it. So here we end up with a vector for coefficients. We can do things like look at our error. And this tells us for every row how wrong our prediction was. Now in a GLM setting, that isn't necessarily very helpful because that is trying to go from 1 and 0 to whatever the logit was. But things like the summary can help you get a little bit more information about a model. Okay, so inputs for a GLM include continuous and categorical variables. So some types of models, you have to convert everything to numeric values first. With GLM, you can chuck character data at it, but of course, having a very, very unique column like postcode might not be very sensible. So you might want to bring that into a smaller range of values. When you provide categorical variables to a GLM, they get transformed by the GLM into dummy variables. What this means is it'll pick a base value. So I always try and make that base value my most common value. And then it'll give a flag for whether it's one of the other values. So if I had eye color of blue, green, brown, gray, then I might make brown my base class because that's the most common. And then my GLM would then have basically some Boolean flags to say whether they're what to do in the event of green, blue, or gray eyes, how that affects the model. Continuous variables should be scaled. So if we were predicting somebody's income, we might have their age and their parents' income. We might have their spouses and some other things. And to get the best model fit when we're doing this, we should make sure that all those values are on the same scale. So age being 0 to 120 is very different to income of 0 to billions. So we need to bring them down into a similar scale. Okay, let's have a look at how we do all of this kind of thing for preparing our data. So one of the most important things you can do is explore your data first. You should be, I don't know if you guys have seen the function pairs, that produces a pairwise scatter matrix. Very, very handy for exploring your data. Caret, which is a package we'll be using again and again, has some handy functions that show you, based on the outcome, the distribution of values, so that you can see what sort of distributions you get by class. There's a lot you can do here, and you should spend a lot of time looking at your data. I think it's when people don't understand what they're modeling, that's when they come out with crazy answers, and nobody wants a model that just doesn't look like reality. So once you've explored your data, identified any potential data quality issues, looked at issues with missing generally, looked for extreme values, that kind of thing, then we go on to the next phase, which is sampling. So I always take a sample before I start deciding what columns that I might need to remove, or how I'm going to handle missings, how I'm going to do the scaling. The reason I do this is it stops information from my test sample leaking into my training sample. So I did some simulations on this, and in about 5% of cases, if I take samples of data, random samples of data, in about 5% of cases, they will have a significantly different mean between the training and the testing samples. So if I had included the the test samples, the test data as well, then my mean would have been very different in my training data, and that would affect the scale distribution, which would affect the fit. And once the fit is affected, then I'm providing then the fit on the training model, on the test data, is going to be improved. It's not going to be improved because the model is better. It's going to be improved because we're leaking information. So I always try and do my sampling first, and then apply the actions to my test data once I've performed those actions on my training data. So caret has a very handy function for when we're working with binomial or categorical variables. The caret function create data partition allows us to specify our sample size. So in this case, 70% training sample. And what it will do is it will maintain the class ratio. So I prefer to work with when I perform sampling, I like to sample with an unbalanced class because my data is unbalanced. If you're trying to predict an outcome that only happens in 1 in 10 situations, and you try and make your data where you fit your model 50-50 split instead, then the rows that you use from the 1 in 10 get massively overrepresented. So the fit of your model overall goes down once it goes into production and is used elsewhere. So I much prefer to work with the same sort of class ratio as I have in real life. So I use the create data partition to do that, and then I can split my data out. So I do a lot of work using caret, and I don't really cover a huge amount of its benefits at the point of building models. I use it here for a lot of the data preparation techniques, but caret really likes you to have your your variables that you're using as your inputs and your variable that you're trying to predict as two separate objects. So we have our variables and our outcome, and we're splitting them, we're getting them into our training set and our test set. So once we have these, we can start acting on them. Okay, so I said earlier we need to scale variables. And there's two common ways of scaling numeric variables. One is min-max. You take how far away from the minimum a given value is, and you divide that by the range in the data. So this gets you a 0 to 1 value, which is really good for things like neural nets. The problem with it is that if you've got a sample of data, there is no guarantee that the minimum and maximum values in your sample data are the population minimum and maximum values. Somebody's always going to come along and be an outlier. And when that happens, you can end up getting strange results. So I tend to work more with z-scores. Z-scores is the distance away from the mean in standard deviations. So this gives us a value that can be plus or minus infinity, but most values tend to be between plus and minus 6. Z-score scaling in R is really simple. So there is a scale function, and you can provide it with two arguments. The center equals true, centers on the mean. So that means that any value that is exactly the mean will have a score of 0. And then the scale works out the standard deviation and the distance from the given point. So something that's 1 standard deviation out above the mean will have a score of 1. Scaling each variable independently like that actually has a really big problem, and it's why a lot of people do scaling before they deal with sampling. And the problem is, when you use that scale function, it doesn't store the mean and the standard deviation. So how can you apply that mean and standard deviation to your training sample or out of time samples or production? You can't. You have to do a big manual process to score it. So Caret comes to the rescue. Caret allows us to not only process a whole set of variables at once and perform the scaling on each column independently, instead of us having to code them all, but it also stores the values for use later. Okay, so when we scale a variable, we get it centered around 0, which is fine. But when we have a data set like this, we've got 10 columns that we need to scale. So Caret has this function called preprocess, and that gives us an object that has that tells us what it's done. And you can go in and refine this, do interesting things. So you can do imputation, principal component analysis, check for zero variance and things. But by default, it just looks at scaling. So we end up with an object that is a list. And it basically tells us the means and standard deviations and what columns it was meant to do centering and scaling on. We can use that with our standard predict function to produce a scaled version of our variables. So now, instead of them all being in different ranges, by using this scaling system, we were able to put everything onto a commensurate scale. And it becomes super nifty, because the next thing you can do then is apply that same scale again and again to different sets of data. So we can now apply it to our testing data very, very simply. So now we're not leaking any information about our testing data. We have a reusable scaling mechanism for new data, and we're able to do it in 2 lines of code. So Caret makes this a very easy process, which makes it easy for you to do it right. Okay, other things to check whilst you're looking at your data. You want to remove highly correlated variables. So there is a function in Caret which has a very sensible algorithm for removing highly correlated variables. You provide it with a correlation matrix, and it will tell you which ones to remove. That's great for continuous variables, and if you have your variables as your categorical variables as factors, you can also look at high levels of correlation between your continuous and categorical variables. The other thing that you want to check for is low variance columns. So this is especially in your categorical variables. If you don't have a lot of change in values, or if the vast majority of so let's say you have a column as to whether a customer is alive or dead in your predictive model. Well, first of all, you should have already removed the dead people, because you can't sell to dead people. But the vast majority of your customers are going to be alive. You might have 97% of your customers alive and 3% dead. That is a very low amount of variance. So I would remove that column. And again, Caret has a function called near zero var, which allows you to set your thresholds and will identify columns to remove. Missings. So imputation is a massive topic all on its own. So I'm not going to go into a huge amount of detail here, but there are some common ways that you can handle missings. The first one is remove the rows of missings. So that makes it easy to use only data that's filled in, but it reduces your sample size. And if you're not working with a lot of data, then that can be a big problem. And it also misses the fact that some missings could be for a systemic reason or give you information about the thing that you're trying to predict where it's missing. Missings themselves can be something worth modeling. With a continuous variable, you can do something like use the mean or the median. Now, I don't recommend doing this generally, because if you use the mean or the median, when it does its lines of best fit, then everything's going to be squashed more towards the center. You start getting all those means end up as basically leverage to on your model. But it's simple to do. You can do imputation, so you can predict. So using the mean is a prediction that the value is going to be close to the mean. We can do something more sophisticated, like actually running a linear regression with other variables to predict a missing value. So again, if we did that using our training data, we would be putting the results of a model that has already been fit on our training data in as something we're going to fit a model on our training data on. So you're stacking predictions and leaking a bit more information and generally fitting that data a bit too much. So that sort of imputation is you can't do it on small data sets, because you need to ideally do imputation on a completely separate sample than your training data for your main model. But it has substantial advantages because the values become realistic and they become more dispersed, so no missing. Your missings don't have substantial leverage. And then something else you can do with a continuous variable is actually make the missings an explicit category, and then perform a binning exercise to group, to consolidate down the continuous variable into intervals. So this reduces information, because a continuous variable hopefully gives us a more refined view per value as to the change in a model. We lose a lot of that granularity, but we're able to then pick up systemic, we're then able to account for missings and give them a specific set of behavior, which can be really handy. Oh, and there's one that I've missed with, as a way of dealing with missings is if it's only one or two columns with missings, you can drop the columns. Okay, so when we build models, I always start my modeling exercise with just two models first of all. One with all my data, with all my features. So that is the most highly overfit model. That is the least generalizable, but it gives us a kind of a view as to the maximum accuracy we could get with a logistic regression on our training data. Then I look at the most predictive variables and just do those. So a simple model is usually better than a more complex model, because it's more interpretable, more generalized, easier to get data for in future. The right answer usually sits in between one or two variables and all the variables. So by starting with these two as my kind of guide points, I can then look at lots of different candidate models and say which one is the right one for the right amount of variables included. One way I can work out the right model, so when we have a full model, we can then use this step function. So stepwise selection can work forward or backwards, or in this case we're going to do both. And what it does is it looks at how much accuracy gain do we get for adding another column to our model versus the complexity of having another column in our model. And you can specify custom functions in there for how that penalty for extra columns works. And in this case, for empty cars, when we're trying to predict the one column, it says that actually you get the most bang for your buck just by using two columns. So it will have gone through and evaluated everything from a single column to 10 columns and identified the right value or a reasonable value. So stepwise selection has its pros and cons. So it's very time consuming, and so you're using a previous model as information to build another model, so you have some information leakage there, which means that some people find it quite a negative model to build because it's an all or nothing, but with this information leakage. So there are some other models that you would then want to consider. So logistic regression, because it's a linear regression, actually has a whole bunch of some really powerful variants. So there is GLMNet and a few other logistic regression-like things that you can run. And they do different things like penalizing extra columns by reducing their impact on the model. And they try a bunch of these different, they're called hyperparameters, so things that control how your model builds to evaluate all the columns but end up with a model where only a few are used or only a few are valuable. And then the other thing when I'm building a logistic regression model, as well as trying some logistic regression variants, is I try decision trees and things, because partition decision tree space can actually be can be pretty quick with regression, and there are a whole bunch of different variants of tree type models, and it's worth evaluating a load of different types of models that are relevant to the task of classifying binomial data when you're doing it. I haven't covered it in a lot of detail here, but you can, the logistic regression fits by ordinary least squares by default, so you can change how it does that fitting in terms of what function it uses to work to evaluate each kind of candidate model behind the scenes. And when you're looking at different amounts of columns, you can change the penalization for adding extra columns. And you should also try common sense models. So common sense models are things that people would expect. So when I do this as a workshop, we work on predicting who survived the Titanic. Because of the iconic women and children first, a common sense model would be to have just gender and age and see how they predict. Okay, so Broom is another R package that is very handy for when you're working with functions like GLM. So it doesn't at the moment work very well with carrots, models, outputs, but it works very well with these basic ones. It has some functions that allow you to produce data frames of different aspects of the model. Now this is really handy because working with lists can be a pain. And if you can get it into a table, you can more easily output it. So Broom is a really handy package to use when you're evaluating models. When you're evaluating a logistic regression, it's like a linear regression. So the more positive a coefficient is, the more it makes your positive outcome more likely, and the more negative a value is, the negative correlation with the positive outcome. You can look at how significant a variable's inclusion is, and how significant the weighting, the coefficient is. So you can often remove the low p-value, the non-statistically significant values. And you can also look at variable importance. So Caret has a function called var_imp, which will produce a metric for each column, each variable, telling you how much it contributes to the model. And again, you can consider removing variables that don't contribute much to the model, because simpler is almost always better. Key metrics. So deviance is a measure of how much error there is. And again, you want lower error. And the AIC is a measure of information captured. So how much is correctly classified relative to how many variables there are. So again, you would try and minimize the AIC. And then one of the things that is particularly close to my heart with logistic regression models is a confusion matrix. So with a confusion matrix, we specify what the actual values were in our binomial outcome, what we predicted based on a 50% probability split by default, and how many we got right. So anything on the diagonal is a correct classification. Anything on the opposite diagonal is an incorrect classification. So on our empty cars, there's not a lot of data. We get 100% accuracy. Now that is completely unrealistic for real life. But this allows us to look at how we're doing, and depending on what type of model you're building, like in what situation, whether you get the positive class incorrectly classified or the negative class incorrectly classified matters. So for cancer, if you're trying to predict cancer, you probably are more happy to predict cancer in situations where they don't have cancer, because then you can treat them, versus saying they don't have cancer when they do. So the confusion matrix really helps you align to your aim based on classification. And you get a whole bunch of metrics, and I often use this balanced accuracy measure in real life when I'm looking at accuracy. So here we had 2 misclassifications in our in our test data, and we thought that they had a positive WT value, and we predicted they didn't. So we incorrectly classified there. Okay, so the slides will be up for you to browse. You can follow me on Twitter, check out my blog. Thank you all very much.